started? I know we did this already, but something to write with, periodic table, calculator, sheets from earlier this week that have your polyatomic ions on it, and then the 2 new sheets that we gave today. So, in no place in particular, here is a statement. It says, in a space station, carbon dioxide exhaled by astronauts can be removed by a reaction with lithium hydroxide. This reaction produces lithium carbonate and liquid water, which can be used for other productive purposes on the space station, like, drinking and stuff like that. Okay? So the first thing I want us to do, and we'll work on this together, okay? I want us to come up with a balanced equation for this reaction. So, what did we say a balanced equation, well, let's start with an equation. What does an equation tell us? Why do we write chemical equations? Why do we write chemical equations? We should probably have that down. Apparently this isn't one of those things that we understand very well.
I just don't feel like talking.
So, chemical equation. What does it tell us? Right, go ahead.
Tells us what is reacting with each other and what they are producing.
Good. What's reacting with what, and then what is it producing? So we start off with what side of the reaction? What's on the left side of that reaction? Reactants. And then the right side of that reaction is? Products. So based on this statement right here, can we determine what the reactants are in this reaction? Okay? Sam? Carbon dioxide is one of our reactants. Lithium hydroxide is our other reactant. Alright? So what are the products of this reaction? This one's pretty easy, so
Lithium carbonate.
So lithium carbonate is one product of this reaction.
And
What else?
Water.
And then water is another product. Alright? So, in order to write a chemical equation, right, we need the formulas for these 4 things. 2 of them should be pretty easy to write. The other 2 contain polyatomic ions, right? So, that is where our practice comes in to begin with. So I want you to write me first an unbalanced equation for this reaction, then balance it. It's not too hard to balance if you've got the formulas correct. So, why don't we take a minute, talk to the people around you, see if we can come up with the formulas for those 4 things, and write an equation that goes along with it. Go.
So, carbon dioxide is CO2. And also lithium hydroxide. Why don't you just stop being such a jerk? Yono say como they balance each other. This here. Yono say como here. Lithium hydroxide.
Your reactants are right. Make sure you find carbonate.
Oh, there it is. I should have known. Why don't you shut up? Alright, you can go. Okay. How do you say lithium carbonate?
C's are there? First one, there's 1.
Oh wait, okay, so we have 3.
There is 3. Lithium, first one, there is 1. Hydrogen.
Hydrogen was the charge on carbonate. Lithium was the charge on lithium. Carbonate has -2, so you have 2 lithiums to balance out the carbonate.
Is that it balanced or is that what we have to balance? Like, is that the answer? I didn't do anything. Like I looked up and that was the answer.
Your carbonate isn't that's not the formula for carbonate.
What is the formula? There's like a 2 and a 3.
Alright! Carbonate's one of your polyatomic ions, right? That's what you looked up on your, not look it up on the grids here, the one that's behind it. Yeah. You see it around the right hand side of the left. Crystal looks like one. Okay. The carbonate one. Alright. So let's go look, okay? So up on the board is the balanced equation that represents this reaction. Okay? So like I said, 2 of them hopefully were pretty easy, right? Hopefully you got these 2 without too much trouble, right? Okay. The other 2 are the ones that contain the polyatomic ions, so they're a little bit harder to go through, right? So lithium hydroxide. You look up lithium on the periodic table and you find out lithium's in what column? Alkali metals. Okay, alkali earth's number 2. But more importantly, how many valence electrons? 1. So what kind of ion is it going to form? 1 plus, right? And then you look up hydroxide on your table of stuff, or that grid that I gave you. Okay, hydroxide being one of your polyatomic ions, right? OH, but it comes with a -1 charge, right? So we said when we're forming the compounds, the positives and the minuses have to balance. So how many of each of these do we need to balance each other out? Just 1 apiece. And that's why the formula for lithium hydroxide just looks like this. Okay? But when we look at lithium carbonate, right? Lithium is still in the first column and it still has a 1 plus charge. But now you find carbonate on your chart or on your table or whatever it is. What's the formula for carbonate? CO3, but more importantly, what charge does it come with? -2, right? So now we got to make, within the formula, within the compound, the charges have to balance. So how many lithiums are you going to need to balance out the carbonate? 2. And that's where the subscript comes from, and that's why this is the formula for lithium carbonate. Does that make sense?
Yeah.
Because in a compound, the pluses and the minuses have to balance. And then it's a matter of just making sure that we have adding coefficients to balance the equation. There it is. Okay? Good there? All right. So the next part of this, and here's the part we didn't get to yesterday. So I'm going to go through this kind of fast, right? But it's still going to be something that you're going to need to know how to do. All right? In an average day, a person will exhale about 20 moles of carbon dioxide. Okay? That doesn't mean much to you, probably, right? So let's put it in terms that we can understand. Like, how many grams of carbon dioxide is that? Okay? So, this is a conversion problem, just like the other conversion problems that we've been doing. So, we start off with what the problem gave us. 20 moles carbon dioxide. The next step in doing a conversion factor problem is what? Put it over 1. Right? Then what? Time sign fraction bar. Right? Now, I always tell you guys to go by the unit, and it's going to be a little bit more important later on today when we do this, right? What unit are we trying to get rid of in this problem? Moles, specifically moles of carbon dioxide, right? What are we trying to end up with? conversion is similar to the conversions that we used to do when we were dealing with elements. Similar, but not exactly the same. Okay? So, first, when we were doing conversions with elements, what number always went in front of moles? 1. And that's going to be the case here as well. 1 is still going to go in front of moles. Okay? But now, when we had grams, where did we get our grams number from, Sean?
Oh, how many grams are in a mole?
Yeah, where did we get that number from?
Oh, periodic table.
We got that from the periodic table, right? So how many grams are in a mole? And we called that number what? Do you remember what we called that number? Anybody? No, that's not the average atomic mass.
Avogadro's number.
Nope, that's the big number. The number is the same as the average atomic mass, but it's in grams. So you said it, how did you say it before? You said it was the number of grams in a mole, right? So we used to call that the molar mass, okay? Similar to that concept, when grams shows up in this conversion factor, we're still going to get the number from the periodic table. But now, do we have one atom to worry about? How many atoms do we have to worry about now? How many atoms do we have to worry about? Just 3. What are the 3 atoms that we have to worry about? Well, 1 carbon, right? And 2 oxygens. So here's what you're going to do. You're going to go to the periodic table, and you're going to look up carbon's average atomic mass. Okay, 12.01. Then you're going to go to oxygen, and you're going to find oxygen's average atomic mass. 16, except how many oxygens are in this formula? 2.
Oh, wait, 32.
Okay, so you are going to add together the average atomic mass of all of the atoms in that compound. This one, it's just 3. 1 carbon, 2 oxygens. When you add the average atomic mass of all 3 of those atoms together, you should end up with 44.01. Okay? So Sean, this is the same idea. It's the number of grams in 1 mole. But now it's the number of grams of carbon dioxide in 1 mole. And we refer to this number as the formula mass. Okay? Same process that we were doing before when we were doing conversions for elements, but now we have to take into account all of the atoms in that formula. Does that make sense? Okay? So you plug that into your calculator, and you should end up with 880.2 grams of carbon dioxide.
Wait, why do we have to just do that?
Well, Lexi, when I told you in the beginning that you exhaled 20 moles of carbon dioxide, did that mean anything to you?
No, I mean, like,
Oh.
how does this relate to the problem?
Well, I just gave you it does two separate problems. Okay? I just gave this to you so we can practice doing this conversion again. Okay? But Lexi, we're going to see over the next couple of days that the ability to turn moles or grams of something into moles of something is an important part of comparing different parts of a chemical equation or a chemical reaction.
Did we already balance that one?
Yeah, we balanced this one up here, right, by putting the 2 in front.
Okay.
So, you run that through your calculator, and you end up with 880.2. But, is that the right answer to this problem? Right. Sam, how many sig digs in this number? 20.0 moles. 3, so we got to round this to 3 sig digs, right? So 1, 2, 3, right? There's the 2. We don't have to round, So a couple ways we could write this answer, okay? You could go 880 with just a decimal point, nothing after the decimal point, okay? Because decimal point at the end, or decimal point makes all the zeros at the end significant, right? Or what's the other way we could do this? Not 8.8, Paige, 8.80, right? Because we got to include that 0 because the 0 has to be significant, right? Go ahead, Kelly.
Do you have to put a decimal point in?
If you, to make that 0 significant, yes.
No, I'm saying do you have to put it, can't you just put 880?
No, because that's only how many significant digits?
2.
That's only 2. Because without the decimal point, that 0 isn't significant. Okay? I know it looks weird to have a decimal point with nothing after it, and people would say, well, that doesn't mean anything. Well, yeah, it does when we're using the decimal point to make it significant. All right, are we good there? Okay. All right. That idea, that's basically what your test is going to be like. Okay? Not test, your quiz on Tuesday. Okay? Not so much making the equation. Okay? But if I tell you to make the formula for lithium hydroxide, you should be able to do that. Or make the formula for lithium carbonate. Sam, go ahead.
Addie asked, how do you name the ionic compound?
Why don't you just, can you like Skype her? I mean, or can we FaceTime her? Or,
That'd be
how do we just FaceTime her? Yeah.
That's like that commercial
Is she
with the kid.
listening right now?
I don't think so. I'm not broadcasting this, but I mean, do you want to just put her on speakerphone? That's actually yesterday my daughter had a conference. There was conferences at my daughter's school, and my son was sick, so I couldn't go. So yeah, we are. That's okay. So yeah, but yeah, I actually attended my daughter's conference on speakerphone. So anyway, yes, Kayla, go ahead.
I have a question on the balanced equation.
Okay.
Does the 2 go for the Li, or does it go for the whole thing?
What coefficients count for everything that they're in front of, right? That's the difference between putting the coefficient here versus putting the subscript right there.
Oh, okay.
That would only count for the lithium, but the coefficient counts for all of it.
Okay.
Okay? Yeah, I mean, if she, yeah. Good.
You know, phones in school.
Ask Mr. Plainasek your question because I can't answer. You're on speaker.
Hi, Eddie.
Typical.
You're on speakerphone. Ask your question.
With the polyatomic ions? Good.
With the polyatomic ions. Eddie? With the polyatomic ions.
Speaker's not on the screen.
Do you want to know how to name the ionic compound? Yeah. So yeah.
Yeah. So when we you don't change the name of the polyatomic ion.
You don't change the name of the polyatomic ion.
You just write them the way that they're written.
You just write them the way that they're written.
Oh, sulfite and sulfate are two different things.
Sulfite and sulfates are two different things.
It depends on what shows up in the formula.
It depends on what shows up in the formula. Okay. Bye. Love you.
Modern technology.
Great class.
Yes, Brittany.
Give her a round of applause for Steve Jobs.
Quiz, will you give us like the forms, how to write like hydroxide?
Brittany, on the quiz, hey, listen. On the quiz, the polyatomic ions and their charges will be there. Okay? Obviously, you'll have your notes when you do your quiz, but on the test, they'll be there as well. So, yeah, at this point, I'm not going to have you memorize any of them just yet. Just, but yeah, you will have them on there. Okay, Kayla, go ahead.
Okay, for hydroxide and
Yep.
sulfate, why are they named that way if they're made of like
It has to do with how many oxygen atoms are joined together with that compound, but it's not a real distinguishable pattern because, like, sulfate has, people that are listening to this will have no idea what we're talking about. This is sulfate, okay? So, even people that were listening have no idea what we're talking about. And this has a -2 charge, okay? And then this, for example, is sulfite, okay? And it just has to do with the number of oxygen atoms that are there.
So will
Okay.
we ever learn how to name them?
Yeah, chemistry-wise, chemistry will give you. Right now, like I said, I'm going to give you the table, and you just read them off the table. Okay. But there is a pattern. But like here, this is NO3, and this is nitrate. Okay. So it's the ATE ending, but this one has 4 oxygens, and this one has 3 oxygens. So
Would it be like too long if you just wrote out like the whole name, like? Because since it's made out of sulfur and oxygen.
yeah. Because that's different. Because Kaylee, that's different than like a compound that has 1 sulfur and 3 oxygens in it that is all balanced charge-wise. And that's why they have different names. So, but like here, going from nitrate to nitrite, the number of oxygens goes from 3 to 2. So like, depending on how many oxygens are there compared to the other ones, that changes the ending of the name. But you don't have to memorize that or anything like that.
I understand.
Pretty good.
Do their charges change between like the
No, they don't, and that's kind of weird because you think they would, but they really don't. And that's another time. That's just like, hey, read it off the table. Okay. All right. Are we ready to introduce the new stuff? Okay.
Yes.
Yeah, that was just review. So,
Oh, you kind of kidding me.
yeah.
I thought I was gonna
This was review of well, you guys didn't get to.
The mole thing was new.
Yeah, the mole thing was new for you guys, but it wasn't new for anybody else today.
Oh,
So,
I felt
So, let's go here. Okay.
Wanna fight?
All right.
Wanna fight right now? Wait. Write this down. 4 o'clock.
All right. So today, I know that the background is boring, but we're kind of in a hurry, so we're ready to go. All right. So the outline that I gave you today, up at the top, it says Introduction to Stoichiometry.
Which one?
The outline. The outline. That's a set of problems. All right. As far as our definition goes, stoichiometry deals with the mass and quantity relationships among reactants and products in a chemical reaction. So we said, right,
Oh, I got it.
okay, right, before, you said a chemical equation does what for us?
It shows what two compounds are reacting with each other and what they produce.
So it tells us what is there, right? But stoichiometry will tell us how much is there. It's a quantitative analysis, right? Quantitative versus qualitative. Okay. So, stoichiometry. Stoichiometry is the calculation of quantities of substances involved in chemical reactions. So there it is again. Calculation of quantities. We're dealing with actual amounts. Where that chemical equation that we wrote before told us that carbon dioxide reacts with lithium hydroxide, now we're going to talk about, okay, if I have 10 grams of carbon dioxide, how much lithium hydroxide am I going to need to react with all of that carbon dioxide? It's a numbers analysis. Okay? Good there? An important part of stoichiometry problems is a balanced chemical equation. A balanced chemical equation, especially the coefficients of a balanced chemical equation, are going to indicate the ratios of the different reactants and products. So a stoichiometry problem is always going to start with a balanced equation, because that's how we're going to talk about the relationship of how much of this one do we need in relation to that one. For example, here is a chemical equation. It tells us what is there at the beginning and what is there at the end. First, for some review, what kind of chemical reaction is that? That's a synthesis reaction, right? We're taking small things and putting them together to make something bigger, right? More complex. It's not that complex, but it's more complex than what we started with. But is that a balanced chemical equation?
No.
It's not. That's a balanced chemical equation, okay? So that chemical equation tells us, right? 1 molecule of nitrogen plus 3 molecules of hydrogen will give you 2 molecules of NH3. Does that make sense?
Yes.
Okay? But can I observe 1 molecule of nitrogen reacting with 3 molecules of hydrogen and creating 2 molecules of NH3?
No.
No. Why not?
Because you.
They're really tiny.
They're really small, right? I can't observe 1 molecule and 3 molecules making 2 molecules. That can't happen. But let's say I started off with 1,000 N2 molecules, right?
They took a picture through the window.
If I have 1,000 of these N2s, how many hydrogens am I going to need? Not 1,000.
6,000.
Nope.
9,000.
3,000. Because what's the ratio between this and this? 1 to 3. If I have 1,000,000 nitrogen molecules, how many of these am I going to need? 3 million. Okay? Sam, go ahead.
So you don't really pay attention to the stuff.
When we're dealing with the quantities, because Sam, this is saying, the equation is saying 1 molecule of nitrogen plus 3 molecules of hydrogen gives me 2 molecules of ammonia. That's what this equation tells us, right? But remember we said the coefficients tell you how many groups there are. Does that make sense? So this is telling, okay, Sam, it's kind of like a recipe, all right? Where if it says you need flour and sugar and water, right? It doesn't really matter, like, you know, like, okay, it's flour. How much flour do I need, right? It would be like the top one, this one is just saying you need flour and sugar and it gives you whatever, right? And what's okay, whatever. You had 2 ingredients, right? You know, this ingredient plus this ingredient gives you this.
Doesn't tell you how much.
But that doesn't tell you, like, how much of each am I supposed to mix together, right? Does that make sense? So the subscripts are like the ingredients. The coefficient tells you how much of those ingredients do you need. Does that make sense? Okay. All right. So let's skip this. Okay. And let's go down to this. Okay. So we're going to start with the most basic stoichiometric relationship, and that is a mole-to-mole calculation. If I give you the moles of one part of that reaction, you can tell me about the other parts of that reaction. If I give you the moles of one of the reactants that I'm starting with, from the equation, you can then tell me, well, how many moles of all the other stuff do I need, right? Just like if I gave you a recipe, and then it said, okay, here's 10 pounds of sugar, you could then use the recipe to figure out how much of the rest of the stuff you needed, right? Does that make sense? Okay. So, there are 3 steps that we go through. 1, balanced equation. The balanced equation tells us the ratio of the different parts of that reaction. So we have to start there, right? You start making a cake with a recipe. The balanced equation is the recipe. Okay? 2, we're going to start off writing whatever they gave us to work with. Okay? A stoichiometry problem is a conversion problem. So we start off writing whatever they gave us to work with. And then we're going to use the coefficients to make a conversion factor to find the other part of that equation. For example, oh look, isn't that convenient? Right? Says, in a space station, carbon dioxide exhaled by astronauts can be removed by a reaction with lithium hydroxide. This reaction produces lithium carbonate and liquid water. Okay? So, let's take a look at this first example, which you guys have at the bottom of your outline that I gave you today. Alright, so here's our first kind of problem, mole-mole problem. So we said that the first thing we have to do is what? What's the first step in doing the stoichiometry problem? Balanced equation. Lucky for you guys, we already figured out the balanced equation, right? So, carbon dioxide plus lithium hydroxide gives us lithium carbonate and water. And we said that we needed to put the coefficient there in order to balance it. Right? Okay. Alright. Next, we write what they gave us to start with. So in this problem, it says how many moles of lithium hydroxide would be needed to remove 20 moles of carbon dioxide, which is the average daily amount exhaled by a human, which we also discussed earlier. Okay? Stoichiometry problems are conversion problems. So, we start a conversion problem with what they gave us to work with. What did they give us to work with in this problem? Specifically 20 moles, and specifically 20 moles of carbon dioxide. That's going to be important from now on. So we start off with 20.0 moles of carbon dioxide, which is what we started our last conversion with, right? The last conversion asked you to go to grams of carbon dioxide. But what is this problem asking you to go to? What's the final answer of this? Well, wait. I heard this somewhere. What unit is our final answer going to have?
Moles.
Moles, but moles of what specifically?
Moles of lithium hydroxide.
Moles of lithium hydroxide, right? So if I have 20 moles of carbon dioxide, how many moles of lithium hydroxide do I need? That's what this question is asking us. So, conversion factor, right? 20.0 moles of carbon dioxide. It's kind of important during the stoichiometry section that you use the formulas to keep track of what we're trying to figure out. I know a lot of times you guys, when we do the moles and grams conversions, you just write moles and grams without the formula. But here the formulas are going to be pretty important. Okay? So, Paige, what's the first step in a conversion problem? Put it over 1. Next step? Time sign, fraction bar. Alright? Nothing changes. Now, when we've been doing these conversion problems in class, I always tell you guys to start with units. Right? So what unit has to go on the bottom of this conversion factor? Specifically moles of what though? Moles of CO2 has to go on the bottom of this conversion factor. Alright? What unit has to go on the top of this conversion factor? We want our final answer to be in moles of lithium hydroxide. Does that make sense?
Yes.
Okay? That conversion factor gets rid of the unit we're trying to get rid of and takes us to the unit that we're trying to go to. Okay? Units first. After we do the units, now we fill in the numbers. Okay? This conversion factor is comparing one part of the equation to specifically one reactant to another reactant. What did we say the equation does for us that allows us to compare one part of the reaction to another part of the reaction? It tells you the ratio. And how does it tell us the ratio, Paige? What part of the equation? The coefficients tell us the ratio. So we go back up to our balanced equation, right? What's the coefficient on lithium hydroxide? 2. So that goes in front of moles of lithium hydroxide. What's the coefficient on carbon dioxide? 1. This conversion factor that shows us the moles of one thing versus the moles of the other thing, or the ratio of the different parts of the equation, we call this the mole ratio. Pretty inventive name for it, huh? But the mole ratio is the important part of a stoichiometry problem, because the coefficients of the equation allow us to compare one ingredient to another ingredient. All right? One good thing about mole-to-mole relationships is that usually the math is pretty easy. Right? So, right, moles of CO2, one in the numerator, one in the denominator, they cancel each other out. The only unit that's left now in our conversion problem is what? Mole of lithium hydroxide, which is what we wanted, right? So then we do our math real quick here, right? So what's our answer going to be? 40.0 moles of lithium hydroxide. So going back to our question, right? It says, now if we know that we have to get rid, right, of 20 moles of CO2, because that's how much we're exhaling every day, now I know how many moles of lithium hydroxide I'm going to need to get rid of all that carbon dioxide. Not just that carbon dioxide and lithium hydroxide react with each other, now I know how much. Does that make sense?
Yeah.
Okay. Question, Paige? Or did? Okay.
Will you ever have to like take stuff from the product side?
That's the next step. We're not going to have time to do that, but you can do that with the products too. The next question, which I think is on your sheet as well, it says, how much water will I make? So you can do the mole ratio with any part of the equation. As long as you have the coefficients, you can create a mole ratio for any part, any two parts of that equation.
So would the next thing be the ratio of CO2 to H2O, or would it be the lithium?
Because you start with CO2 still. Okay. All right, so for quiz on Monday, you will not have to do any mole ratios on the quiz on Monday. It's just polyatomic ions, formulas, and stuff.
Thank you.
Then you will have to convert like grams into moles for compounds, but you won't have to do moles to moles. Then after the quiz, we'll get into stoichiometry a little bit more. Talk about a different kind of problem. For the weekend, the problem set that I gave you today, I gave you 2 sheets. One of them had problems on it. The answers to those problems are posted online. They are mole-to-mole calculations. So check them out. Okay?
Got you.
Good job, everybody. We made time. Well done. I mean, I don't want to say anything, but somebody who was on speakerphone before wasn't here today.